Alright, we have added a new member to the Vortex family, and here we have a dual interweave torus. And just to show you the geometry here is, so we come from here, it goes down counterclockwise, and it comes out this bottom portion and starts wrapping around this coil. And then it goes down clockwise, goes in and comes out here, and then goes down and around counterclockwise, right? So it's kind of doing this thing here where it goes back up, comes in. So it's doing this crazy Ouroboros type geometry here, whereas this one just goes down and around and comes out, keeps doing the same thing over and over again. So I'm not sure what more this accomplishes yet. It definitely has different geometry. I don't know any plus sides to having one side go down clockwise and the other side counterclockwise, whereas this coil in particular goes down counterclockwise and down counterclockwise. So that's where we get a key difference in the geometry. Again, I don't know what differences that is really going to make, but what we will do is we'll have our signal generator hooked up across a capacitance and the coil to make a little LC circuit. We'll measure this resonance and we'll measure this resonance. This just has the secondary. I haven't put the primary on yet, but this is the same form as these two. So this is about half of this length of wire. So we got that hooked up to the signal generator, and you can see how I just gotta get this hooked up right. Alright, here we go. So this is our signal going in, and this is what the oscilloscope is registering around the coil. So we can see how the waveform changes, and as we increase the frequency, you can see that the waves start to constructively and destructively interfere, resulting in a spot when the coil enters resonance, which is right around here. So say we freeze that, blow that up, and you can stretch that out. Let's see, this is a little more accurate. So it's 14 microseconds, right? So it's 28 microseconds, and this says we're about a little short of 35 kilohertz. So go to our trusty calculator here, and we'll go 1 divided by 0.00028, right? And we come up with 35.7 kilohertz. So that is that frequency. And now we can measure this one. Well, before we go on, let's show how. Now when we see this capacitance here, when we pull the capacitance out, it's 500 picofarads. Changes the resonance, right? So now it's out of resonance. To get it back in resonance, we have to increase the frequency. So by adding capacitance to the circuit, we have to decrease the resonant frequency to get it, or decrease the input frequency to get the coil back into resonance. So now we'll do the same for this coil. So remember, this one was around like 35.7 kilohertz resonant frequency. So now we'll get our probes hooked up on this one. do with one hand. So we got that hooked up now. And we'll see that we don't have any resonance. Take down the frequency a bit here. And let's see. So this is not hooked up. It's doing some funny things. Alright. So we'll put the probe here now, right? Because that's why it doesn't look right. So at low frequencies, you can see the coil does essentially the same action it did before, right? There's not a real difference in how it resonates. Now when we go up in frequency, we get constructive and deconstructive, and our constructive frequencies happen on harmonic scales. So we'll zoom in here a little bit. We'll find the best peak to peak, right? So right around here is when it hits resonance. And we can already tell that the wave is a lot bigger. So it says between 28 and 25. So let's just call it 26.5 microseconds per division. So we'll call it about 52, huh? So 1 divided by 0.000052. Get a resonant frequency in 19.2 kilohertz. Right? So this one was about 35.7, 19.2, same capacitance, double the wavelength. So it has a different resonance. It resonates in lower frequencies, which is good. What Tesla was doing is he was using low frequencies, very VLF radio waves essentially, but when they're low frequency, they don't resonate or radiate into the air like radio waves do. Instead, they can resonate the earth very well, and you can use that to transmit electricity wirelessly and produce a resonant asymmetrical system where you can light up a bunch of light bulbs off one power supply that would take to light one light bulb. So through resonance, you can set many things into oscillation. But so that is the coil, and it's got a difference in wavelength, and we'll put a primary on here and an opposite direction, and we'll see just how much voltage gain we get with the different design, and we'll see if there's any extra voltage gain or any plus side to using a design like this versus a design like this, because right now these are easier to wrap. This is not so much, and I mean, with two forms, you know, I could make two of these, transmitter and receiver, whereas with two I only have one. So plus side is it can do counterclockwise and clockwise on the bottom, which is neat for a coil, whereas this is the same on both sides. So I'm not sure which one's better, if there are any better things about it, or if it's just a different geometry, thus it makes a longer wavelength while keeping the same type of vortex. So yeah, I'll be putting a primary on here, and we'll be measuring the voltage gain later on. Thanks for watching.